Okay, welcome everyone to this week's QTFMS talk. Today we are hosting Brandon Rayhaun from Princeton Institute of Advanced Studies. He's going to talk about his recent work on spin-flux duality. Brandon, thanks a lot for accepting our invitation. It's a pleasure to have you today. You can take it away.
Great. Yeah, thank you very much for having me. So I was asked to talk about this recent paper that I wrote with Fedor Popov and Zohar Komargatsky. And so the basic idea of the talk today is summarized in this sort of little diagram. The idea will be to use a few tools of the trade in quantum field theory. Some may be more standard, like symmetries and anomalies, or the irreversibility of the renormalization group flow, and some slightly less standard, like I'll describe some interesting phenomena that can happen when you have parameter spaces, to learn new things about defects in old examples of quantum field theory. Okay, so I guess the first order question I have to address is what is a defect? So sort of concisely, a defect is a modification of a quantum field theory along some locus of spacetime. And a sublocus of spacetime. And the most sort of common examples of defects that one encounters, for example, in quantum field theory courses, are just local operators. These are modifications of a quantum field theory at a particular point in spacetime. But nothing stops us from considering extended objects as well, such as line defects or surface defects or membranes. And in fact, they do furnish interesting probes of the physics. Um, so good. So that's what is a defect? So why should we study them? Um, One answer to this question is simply that they have a lot of really nice applications. Uh, so for example, if you're a high energy theorist, you might be interested in Wilson and Hooft lines of gauge theories because they're useful for diagnosing what phase the gauge theory is in. They're sort of order parameters. Uh, if you're a condensed matter physicist, then line defects, for example, can be thought of as modeling sort of impurities in some kind of material that you might be studying. Um, for maybe a more mathematical application, also, of course, replete with physical consequences, is so a special case of defects are topological defects. So these are defects where if you insert them into correlation functions, then the correlation functions don't sort of depend on precisely where you place the defect. You can sort of smoothly deform the defect around, and the correlators won't change as long as you don't move the defects through some charged operator. And it's been a kind of common story of the past decade or so that one should understand topological defects as furnishing some kind of generalized notion of symmetry. So these have tons of consequences. Arguably, even more interesting are not necessarily topological defects, but these are much harder to study. But that'll be sort of the focus of this talk is mainly trying to learn things about non-topological defects. And if we include things like boundary conditions under the umbrella of extended objects, just sort of codimension 1 defects if you'd like, then you get a ton more applications. For example, everything from branes and string theory, finite size effects, if you're interested in statistical mechanics. The list goes on and on and on. Okay, so they do have many nice applications, but more abstractly, one of the main reasons I'm motivated to study them is simply that they're part of the defining data of quantum field theory. And if they're part of the defining data, then if we're claiming to know what quantum field theory is, then these are the kinds of objects that we should have to be able to contend with as well. So they're useful in our general quest to understand what quantum field theory is. Okay, so that's maybe why. And now I should tell you what. So what do we want to understand? Well, there's many questions that you can ask. In this talk, I'll mainly be interested in a very coarse question that you could ask about defects. Namely, suppose I sort of give you a defect in the UV. Let's suppose the bulk theory is already at a fixed point. It's already conformal field theory, let's say. And I insert some kind of defect in the UV. What does that defect look like at long distances or at small energies? So given So in other words, maybe people sometimes draw the following picture. You have some CFT plus some defect in the UV, and you trigger an RG flow by adding some kind of a local operator along the locus of the defect. And at long distances, you should expect to get some defect in the IR. And the question is, what does this look like? And I'm not particularly interested in the details of what this defect looks like. I'll mainly be interested in determining which of the following scenarios is realized. So there's a few possibilities. So one possibility is simply that at long distances, the defect kind of disappears. Or maybe a little bit more precisely, the defect flows to the identity defect in the IR. So we call this trivial. Defect flows to a trivial defect in the IR. So in this scenario, if you're an observer that's sitting at long distances away from the defect, there's not really much you can do. Maybe if you try and detect the defect by measuring local operator correlation functions or something like this, there's not much you can do that to be able to see the defect at all. By the way, let me restrict to line defects in this discussion just to make things simple. Okay, so that's one kind of boring scenario. Another also somewhat boring scenario is that the defect might decouple in the IR to some decoupled conformal field theory that doesn't interact with the bulk in any particularly meaningful way. Because we're talking about line defects, this would mean that the defect is flowing to a 1D conformal field theory, but there's not really many 1D conformal field theories. They're all topological, and they're all just simply labeled by the number of ground states that are there. So, well, I'll call this TQM. This stands for topological quantum mechanics. So in this scenario, the defect basically flows to a decoupled qubit with k ground states, something like this. Or if you like, in this kind of notation, sometimes people write this by saying that the defect's flowing to a direct sum of identity line operators. K sum of identity operators. Okay, so in this scenario, there's also not
Can
much
I
that,
ask a question? So,
yeah.
so if the defect is non-trivial, usually the one-point functions pick up some non-zero value, right? But in this case, it wouldn't pick up anything because it's not interacting. Is that correct?
Yeah, there won't be one-point functions here. So the one-point functions are picked up are going to come into play in the fourth scenario that I'll tell you about,
Hmm.
which is that when the defect becomes a conformal defect, a non-trivial conformal defect. Technically, all of these are conformal defects, but here I mean just an actual conformal defect.
Okay.
Um, so yeah, people are a little bit fast and loose with the word trivial and things like this. So technically, this defect I would say is non-trivial, but its one-point functions still vanish. So yeah, basically
Okay.
this little exposition here is to try and be super precise about the terms to avoid the kind of common pitfalls of language in the subject.
Okay.
Yeah, yeah, good. Thanks for the question. Um, okay. Um, so by the way, in this scenario, for example, if you uh, considered the theory on some compact manifold, spatial manifold, with the line defect piercing the spatial manifold at a point, so forming some kind of point-like impurity, then, for example, you would see a ground state degeneracy when you look at uh, the Hilbert space associated to that background. So that's one signature that you would see in this scenario. Another possibility is that the line defect flows to some topological line operator. So we call this topological. And then finally, as was anticipated, the kind of maybe most interesting scenario is that the defect becomes conformal at long distances. And then you start to see non-vanishing one-point functions in the presence of the defect. Okay, so technically, you have a picture like this where each case includes the previous case as a special case. TQM, topological, conformal. But typically when I use these words, I'll mean, so for example, when I say a topological line, I'll mean a topological line that's not trivial nor is decoupled, let's say. But in any case, I just want to flag this. Okay, so right, so the goal is going to be given some examples of defects in quantum field theory to determine which of these scenarios is realized. This seems like it should be a very easy question to answer. But let me just point out that, for example, one of the Millennium Prize problems is a question of this sort. So it's one of the Millennium Prize problems is to prove that Yang-Mills theory in four dimensions is a trivially gapped theory. So in a sense, well, so it's a kind of version of this question, of course, without defects, just applied to bulk quantum field theory, but it's kind of version of this question where you're asked to prove that Yang-Mills theory realizes a scenario like this first one here. So in Yang-Mills theory, we don't have any kinds of anomalies that can be used to help us to answer that question or any other trick up our sleeves. But for the theories that I'm going to tell you about in this talk, there will be some other tools that we can use. So the question will become a little bit easier.
Can I ask
Okay,
something about the Yang-Mills problem?
sure.
Uh, isn't there like an anomaly between the instanton -1 from symmetry and the center symmetry? I mean, isn't that useful for understanding? Maybe.
Sure. So the Millennium Prize problem is about Yang-Mills theory with the theta angle set to 0.
Oh,
And at that special point, uh, there's no kind of anomaly. I think what you have in mind is that so there is this kind of notion of an anomaly in the space of coupling constants, uh, which we'll see examples of that applied to defects later in the talk. Um, but another sort of more pedestrian way to say it is that at theta equals pi, there's some kind of mixed anomaly involving time reversal and the one-form symmetry. So indeed, at theta equals pi, there is an anomaly, and you can conclude that it's non-trivial. But at theta equals 0, there's no anomaly that you can use to help you, and so it's
hmm.
a little bit more difficult to sort of to prove.
Okay. Yeah. So if you consider the theta angle as the background field, the anomaly is only at the specific value of the background field.
Well, no, if you consider it as a background field, then really you're probing sort of the entire, one parameter
Oh,
family
oh
of
yeah.
Yang-Mills theories.
Hmm.
Uh, but it just doesn't have any particular implications for theta equals 0.
Okay, okay. Yeah, I
Yeah,
see.
good. Thanks for the question.
Thanks.
Okay, so now I should try to tell you how we're going to constrain these defect RG flows. So one tool so as I said, there's going to be three basic tools that I'll try to explain how to use, and I'll explain them in turn. The one I want to start with is I want to use RG monotonicity theorems. Monotonicity theorems. So the most famous example of an RG monotonicity theorem, and I think probably the first, is Zamolodchikov's C theorem. So what it says is that if you have some kind of flow between 2D unitary, let's say compact CFTs, well, there's this quantity that you can associate to a CFT known as its central charge. It appears all over the place in 2D CFTs. It's one of the most important invariants that you can associate to a 2D CFT. Perhaps kind of operationally, the most convenient definition is that it arises in the two-point function of the stress tensor. It's the leading term. Okay, so what the C theorem says is that the central charge of the theory in the UV is always greater than the central charge of the theory in the IR. And so this theorem rules out infinitely many putative RG flows. And it's especially useful when you're considering RG flows where the theory in the UV has a small central charge, because then there's a very limited menu of options for what the IR theory could be. Okay, so that's maybe the first example, but since the C theorem, there's been generalizations that apply in general dimensions and also to defects. So for us, I want a version of the C theorem called the G theorem. And it applies to specifically to line defects in general dimension. And so what's the idea? So the way that you would like to define G is you'd like to define it as the sorry. You'd like to define it as essentially the expectation value of the line operator when it's wound into a circle of radius r. This has a bit of scheme dependence to it. And so the way to sort of extract the universal part of this this expectation value is to act with this operator out front. And when you do this at when the bulk is at a fixed point, or when the defect's at a fixed point, then you get some universal number, and that's what we call the G function. And the G theorem says, much like the C theorem, that G decreases monotonically under defect RG flows. So this is specifically for situations where the defect flows, but not the bulk. So the bulk is some fixed CFT throughout the problem. Just want to stress that. So for example, let's go through those various scenarios and say what G can be. So for a trivial defect, which is just the identity operator, G function is simply 1. Right? In that case, the expectation value, well, yeah, I think that's pretty self-explanatory. For a decoupled topological quantum mechanics with K ground states, the G function is simply K itself. You should think that this expectation value of the line defect is essentially the S1 partition function, the thermal partition function of this topological quantum mechanics, and that just gives you the number of ground states. For a topological line, G is sometimes called the quantum dimension, and it can generally be I think any real number. Well, it might need to satisfy some algebraic properties or something like this, but let's just, a priori, let's say it's any real number. However, it's a real number that must be greater than or equal to 1. And sometimes this is called the quantum dimension of the line defect, specifically when the line defect is topological. And for conformal defects, in principle, you can get any positive real number.
I have a question about the C part. Shouldn't the quantum dimension be an integer because sometimes it's related to the dimension of the defect Hilbert space?
No, quantum dimensions do not need to be integers. For example, in the Ising CFT, there's these topological lines. There's a Z2 line, and there's this Kramer's 1A duality line. And the quantum dimension of the duality line is square root of 2. So they're not directly related to the actual dimension of a defect Hilbert space.
I see.
It sort of appears sometimes in various asymptotic formulas for the asymptotic density of states in of defect Hilbert spaces, but they're not directly a dimension in that way.
Okay. So it's not directly dimension, so it doesn't have to be an integer. Yeah.
It doesn't have to be an integer. Yeah.
Yeah. Okay, thank you.
Yeah, thanks for the question. Okay, so let's just see an example of how to use the G theorem to constrain the IR phase of a defect. So there's this broad class of examples called pinning field defects. So suppose you have some CFT in the bulk, and it has some local operator O, whose scaling dimension is less than 1. In this case, this local operator is, well, it's relevant with if you were to use it to deform the bulk, but because it's dimension less than 1, it's also relevant even if you just integrate it along a line in space-time. So it's relevant with respect to line defects. So you can start with the CFT and the UV plus the trivial line. And you can trigger an RG flow using this local operator by integrating it against time, let's say. And you'll land in the IR on some defect. What can we say about this defect? Well, by the G theorem, so notice that the line defect in the UV is the trivial line. So GUV is 1. And that means that by the G theorem, GIR has to be less than 1. But if we look up here at this list, the only scenario which is capable of realizing a G function which is less than 1 is this last scenario. And so in particular, the G theorem allows us to conclude that pinning fields flow to conformal lines. Okay. Good. Any questions about this so far? Okay. So next I want to explain how to incorporate symmetries and anomalies into this game. So let's, for concreteness, specialize to 3 dimensions, bulk. And also for concreteness, I want to only consider ordinary zero-form symmetries. So in principle, you could consider things like non-invertible symmetries, higher form symmetries, but let's keep things very simple and just suppose we have some zero-form symmetry in the bulk, some standard symmetry. And I want to consider line defects which respect this symmetry in some sense. Preserve G. So what does this mean? So the kind of modern way of formulating a zero-form symmetry is that zero-form symmetries, the elements of the group define topological, in this case, since we're in 3 dimensions, topological surfaces. In general, it'd be a codimension 1 topological defect. Topological surfaces that one might write like this. And so when I say that I want my line defect to respect the G symmetry, what I'm asking for is that if I take my line and I sort of thread the surface through the line, then it should be possible to find some topological point junction xg for each element of the group, such that basically I can draw this picture. So this demanding that this junction be topological means in particular that I can sort of move the surface up and down along the line defect without altering correlation functions. Again, provided I don't move the surface through some charged operator. And if you'd like, this condition is sort of equivalent to the following condition. So I want to demand that if I take my line and I take a hollow cylinder of my G surface and I squish this cylinder onto the line, then I want to get the same defect I started with back, as opposed to a different defect. So in a sense, the defect is invariant under the action of sort of fusing a surface onto it. This is the definition of what it means for a line defect to be symmetric with respect to G. Okay. And now I want a notion of a defect anomaly. So let me crucially emphasize that you can discuss the anomalies of this zero form symmetry in the bulk theory, and you'll get some answer, but that's not what this definition is going to be about. In particular, all the examples that I'll discuss, G will be non-anomalous in the bulk. So, for example, it'll be possible to consistently gauge it in the bulk. However, when you insert the defect, in general, there could be some contributions to the anomaly which come from the defect. And those are the things that I want to discuss. So to prepare for this definition, let me remind you that ordinary local operators, genuine local operators, transform linearly under zero form symmetries. I say linearly in contrast with projectively. If the dimension of the theory is greater than greater than 1. So in quantum mechanics, we're sort of taught in school that states, for example, can transform projectively, but in quantum field theory with d greater than 1 dimensions, the local operators always transform linearly. And the ultimate reason for this, in the language of these surface operators, is that when I fuse two topological defects together, there's no phases that can arise here. So projective representation is a situation where when you sort of multiply two symmetries together, then you get the product symmetry back up to a phase. But for surface defects, for example, there cannot be any phases because it doesn't mean anything to sort of rescale a surface operator by a C number. They have a kind of canonically defined normalization. So because of this, when you act on local operators, say by encircling them with some spherical shell, and you collapse the spherical shell onto the local operator, this action of the G symmetry on the local operators is linear. But suppose now that I attempt to fuse two surface operators in the presence of a line defect. Well, now when I do this, I don't just have a surface operator. I also have this topological point junction. And in contrast with defects of dimension greater than 0, defects of dimension 0, i.e. point-like operators, can be rescaled by a C number. So it does make sense to sort of rescale these things by phase. And so now here phases can appear. Get some phase like this. Okay. Now, this phase can't be arbitrary. So the fact that when you take 3 surfaces, let's say, and fuse them 2 at a time in different orders, the fact that that is associative implies that this psi is a 2 cocycle. So sometimes people write this by saying d psi equals 0. On the other hand, these choices of junctions, xg, there isn't really a canonical choice. So I could have chosen xg, but you could have chosen x prime of g related to my choice by some C number alpha. And this has the effect of sort of shifting this 2 cocycle by an exact 2 cocycle. So in other words, so this is sort of an unphysical thing. It's not a universal thing. So we only care about the 2 cocycle up to shifting it by exact 2 cocycles. And this is precisely the problem of group cohomology. So this what these two things tell you together is that the universal part of psi is an element of the second group cohomology of G with coefficients in U1. Okay, so the sort of summary is that and this is what we call the line defect 't Hooft anomaly. So the sort of summary is that if you have a zero form symmetry G and a line defect that respects it, in general, you can incur phases when you fuse symmetry surfaces in the presence of the line. And these phases, in general, specify an element of the second group cohomology of G. And that's the thing that we call the defect 't Hooft anomaly. And so what are some consequences of having this anomaly around? Well, for one thing, it must be matched under RG flows. So if the defect in the UV carries some non-trivial 't Hooft anomaly, then the defect in the IR must also carry it. One sort of intuitive way to argue for this is that this second group cohomology is a kind of discrete group, or it's even a finite group, let's say. And because under RG, the physics sort of changes continuously, there's sort of no way for this 't Hooft anomaly to change. It would have to jump, and that's a discontinuous process. So the anomaly must be reproduced in the IR, and in particular, since the trivial line defect does not carry any kind of defect 't Hooft anomaly, this implies that if DUV has some non-trivial 't Hooft anomaly, then it flows to something non-trivial. So it could still be, decoupled, topological, or conformal, but it can't be trivial.
So we can immediately say that the pinning field defects in the ON models cannot have anomalies.
That doesn't follow from this, right? Because so the pinning field defects, yeah, good. You could flow to a conformal defect while having a trivial 't Hooft anomaly. So the implication is only in one direction. So it's like if you have an anomaly, then you're non-trivial, but just because you're non-trivial doesn't mean you have
Yeah, I see,
anomaly.
Yeah. Yeah, right. But they cannot have anomalies, that's for sure, right? Because we start from a trivial defect in the UV.
I see what you're saying. Yes, I think that, yeah, I think that's one, yeah, that's a good argument. So indeed, so because you're starting from the trivial defect in the UV,
Mhm.
let's suppose the local operator you deform by respects some G symmetry, then indeed, I think this would argue that, yeah, you cannot have any defect of anomalies. Yeah, thanks.
I see. Yeah, thanks.
Yeah, very good point. Um, good. And another consequence, for example, is that if you look at the Hilbert space of local endpoint operators and you consider the action of the G symmetry on these local operators, essentially by sort of collapsing a spherical shell of the symmetry surfaces onto local operators, then because of these phases that you get when you fuse symmetry surfaces in the presence of a line, what you find is that this sort of defect Hilbert space transforms projectively under G. And in particular, that means that there's ground state degeneracies. And that's for the trivial reason that any group, any projective representation of a group must have dimension greater than 1. So there's no one-dimensional projective representation of a group. Okay, so these are just two sort of easy consequences. So let's do an example. Let's consider the O3 model in the bulk. So this is a theory of 3 real scalar fields. Uh, Schematically, the action takes this form. I'm just being very schematic. And if you tune the, uh, if you sort of tune parameters in this model, you can tune it to a fixed point that defines a 3D CFT. So this is the model I want to study. It's very strongly coupled. The line defects that I want to consider in this model are a sort of analog of Wilson lines in gauge theories. So in particular, for any half integer spin S, I want to define a line operator that's defined as the trace of the path-ordered exponential of the following thing. Let me be a little bit more clear. And for the future, well, yeah, let me just stick to this for now. So here, these TA are matrices that represent SU2 in the spin S representation. So for example, when S is equal to half, these are just Pauli matrices. Okay, so this is some kind of Wilson line. And you could ask, what does this Wilson line flow to in the IR? This isn't the most convenient description of this line operator. It turns out it's useful to pass to a kind of different description, which is the following. So we take our action to consist of the action up here in the bulk for the O3 model. And I want to add the action of a spin S qubit, so just a a decoupled topological quantum mechanics with 2s plus 1 ground states. And I want to couple this qubit to the bulk as follows. So just imitating this Wilson line coupling. Like this. So here, these are the local operators in the decoupled topological quantum mechanics that implement the SO3 symmetry. Okay. So this formulation of the problem makes the anomalies much more transparent. So if I go all the way to the UV, I can basically forget about this coupling term. And I just have a decoupled topological quantum mechanics, and this defect 't Hooft anomaly that I want to calculate is just an ordinary anomaly of this quantum mechanics. And so that's very straightforward to calculate. So the relevant facts are that what's the global symmetry? So the global symmetry is SO3. So the bulk has an O3 symmetry, but the defect sort of breaks this O3 symmetry down to an SO3. And good. So that's the global symmetry of this decoupled topological quantum mechanics. What's the anomaly? Well, the anomaly is just you have to determine whether or not the states in the Hilbert space transform projectively under this global symmetry. And so, of course, we know that for half integer s, that's precisely what happens. The states in a qubit, in a spin s qubit, transform in a projective representation of SO3. And so we conclude that there is an anomaly, whereas for integer s, you transform in linear representations of SO3, and there's no anomaly. So in particular, for half integer s, there is a defect 't Hooft anomaly. And so WS flows to a non-trivial line defect. For integer s, so far we can't conclude anything. Now, again, this is a somewhat weak statement because a priori it could still flow to a decoupled line or a topological line or a conformal line. But now we can also incorporate the G theorem into our analysis as well. So so let's specialize to s equals 1/2 for this. So in this case, what's the G function of the UV? The UV defect is a decoupled quantum mechanics with 2 ground states. So in particular, the G function in the UV is 2. The G theorem implies that the defect in the IR has to have G function less than 2. And so this immediately rules out a decoupled defect, because remember, a decoupled defect in the IR would have G function being an integer. And the only integer less than 2 is 1, but we just ruled that out via this defect 't Hooft anomaly because a decoupled defect with G equals 1 is just a trivial defect. So the defect and the IR is not decoupled. Um, but furthermore, O3 model doesn't have any one-form symmetries. So I assert this confidently, but so I should more carefully say that it's not known to have any one-form symmetries, and it's highly likely that it doesn't have any. But this is maybe a bit of a conjecture. But if we assume this conjecture, then that in particular means that it doesn't have any topological line operators. So because it doesn't have any topological line operators, that means in particular that this IR defect for this S equals 1/2 qubit is not topological either. And so
I have
that
a question about this conjecture, sorry. So can't I take any symmetry in the O3 model and gauge it on a codimension one submanifold to get a one form symmetry? Sorry, to get a one form, I have to gauge on a codimension too. But can't I just construct a condensation defect to get a symmetry?
um
Or is there an obstruction? That's why this is a conjecture.
let me think about that. So you want to gauge along a line. I haven't thought
Yes.
about how to do that before. It seems not possible, right? Because uh like the only known symmetries you have are zero form symmetries. Those form surfaces.
Oh,
How do
yeah.
you gauge a surface just along a line? It seems probably like it's not possible. I think in
Yeah.
general, when you gauge along some locus of space-time, the symmetry operators have to have a dimension that's smaller than that, than the dimension of that locus of
Yeah,
space-time
yeah, yeah,
gauge.
that's right. Yeah, doesn't seem plausible.
Yeah, so that construction doesn't immediately work. Um, but if you know how
Yeah,
to
yeah, I
construct
see.
any lines, I'd be very interested.
Yeah, yeah, I see your point. Yeah, that makes sense. It was too naive. Yeah.
But thanks, yeah, thanks for the question.
Yeah. Yeah.
So, but now we've ruled out all three possibilities besides the last one, which is that that it's conformal. So, by the way, I should have also just a nomenclature thing. This description of the defect is called a spin impurity. Because you can think you have some QFT and you take some qubit and you realize it as some impurity in your QFT. So this problem of showing that the spin 1/2 spin impurity in the O3 model is conformal is sometimes called the boson-Kondo problem. Okay. So this is an example of how you can use symmetries and anomalies plus G theorem to learn something about defects in the O3 model. And then the last tool that I want to tell you about is what is sometimes called an anomaly in the space of defect couplings. So, by the way, should I plan to stop directly uh, at the hour or?
No, if you want to continue, you can go on. We usually have talks like that extends an hour, so that's okay.
Okay, yeah, I'll try not to go too long, maybe like an extra 10, 15 minutes.
Yeah, sure. As much as you want to.
Okay. Anyone is, of course, welcome to leave. Um, good. Um, so I want to explain briefly this notion of an anomaly in the space of defect couplings. Uh, but rather than sort of try to develop a general theory, which is, I think, safe to say, work in progress, let me just illustrate the main sort of phenomenological features in a concrete example. So for reasons that will become clear, I want to focus on the abelian Higgs model in 2 plus 1D. So this is the theory of a U1 gauge field. With field strength little f, coupled to a charge 1 complex scalar. Something schematically like this. However, let me just say that the stuff that I tell you now actually will apply to abelian gauge theories with pretty general matter content. Also in higher dimensions, there's versions of this as well. Good. So what's the line defect that I want to focus on? I want to focus on vortex lines. So these are defects, which are defined as kinds of disorder operators. So disorder operators are kind of like operators that are not defined by inserting some kind of expression built out of the fundamental fields into the path integral, but rather they're defined by modifying the field configurations that you integrate over in the path integral so that they have kind of singular boundary conditions along the locus of the line defect. So specifically, the vortex line is defined by doing the path integral only over gauge field configurations, which have some fixed holonomy alpha along when you link with the line. So if I integrate the gauge field along this line C, I want to only do the path integral over gauge field configurations such that this holonomy is alpha. Okay, good. And so let me just comment that, so yeah, first comment is that this is a kind of continuous family of defects. There's an S1 family of line defects. And why S1? It's simply because holonomies are only defined modulo 2 pi. So alpha is a 2 pi periodic parameter. So that's comment number one. Comment number two is that these line defects all preserve some of the global symmetry. So the abelian Higgs model in 2 plus 1D has in particular what's known as U1 magnetic zero form symmetry. If you'd like, the sort of surface operator that implements the symmetry is just obtained by integrating the field strength F along the surface. Okay, so this is basically a kind of canonical U1 symmetry in any abelian gauge theory that doesn't have dynamical magnetic monopoles. And it turns out that each of these line defects V alpha preserve this U1 magnetic. So we have these two facts that there's some kind of parameter space of line defects with some non-trivial topology. So there's this S1. And we also have that the line defects preserve a global symmetry. And the basic statement of anomalies in the space of defect couplings is that there's a tension between these two things. If you'd like, there's a kind of mixed anomaly between the 2 pi periodicity of this defect parameter and the preservation of the U1 symmetry. So if you were trying to detect an anomaly, a mixed anomaly between two ordinary symmetries, one way that you could proceed would be to couple one of them to a background gauge field and then observe that the other one is violated. So we can do something similar here. So suppose that we want to couple to a background gauge field A for this U1 magnetic symmetry. The way that you would do that in the absence of this vortex line is you would simply add the following term to the Lagrangian. So this A is a background gauge field. This is to be distinguished from the dynamical gauge field in the problem, which is little a, and whose field strength is little f. Okay, so the way that you would ordinarily couple the abelian Higgs model to a background gauge field is you would take the original action and you would just simply add this term. However, in the presence of an insertion of this vortex line, V alpha, it turns out that this isn't quite gauge invariant under gauge transformations of the background gauge field. And you need to add a term to restore gauge invariance under background gauge transformations. And that term that you add is simply the integral of A along the locus of this line, L1. So this is in the entire bulk manifold, and this integral is along just the line. Okay, but now you can see that if I, for example, compute the partition function of the theory, in the presence of this background gauge field, and let's say with a vortex line V alpha inserted, then if you try to study whether or not the partition function is 2 pi periodic still, then you find that it almost is, except that that 2 pi periodicity is violated precisely by a Wilson line in this background gauge field, so by this phase here. So so if you'd like, we sort of coupled to a background gauge field for the global symmetry, and then we witnessed that the 2 pi periodicity is violated. That's a kind of signature of a mixed anomaly between the 2 pi periodicity and this global symmetry. You could have also done things the other way around. Namely, you could have coupled the parameter space to a background gauge field. What does that mean? Well, here that would just mean that you allow this defect parameter of the vortex line to have some kind of profile in time. So you allow it to explicitly depend on time. And then you would ask whether or not, let's say, you would then take this partition function and perform this U1 magnetic zero form symmetry on it, and you would ask whether or not the partition function is invariant. And again, you find that it is not. I'm going to get the sign wrong, probably. But that's, let's see. Something like this. You find that you get a phase if you allow this. So let's say, sorry, I should have said, let's say that the manifold that I'm computing this partition function on is S1 times some 2 manifold, and that the line is wrapped along the S1. So in particular, then I can allow this defect parameter to wind along the thermal circle. And let me call W the winding number, so it's an integer. So if you give the defect parameter a topologically non-trivial profile, then you see that you violate this U1 magnetic symmetry. So this is sort of like detecting the anomaly the other way around. Okay, so that's the notion of an anomaly in the space of coupling constants, or defect coupling constants. And just like ordinary anomalies, they have a variety of implications. So one is, of course, that they must be matched under RG and across dualities. More on this in a second. And another thing is that so usually anomalies signal that something non-trivial is happening in the physics. When you have an anomaly in the space of defect couplings, what you can conclude is that there's some value of this defect parameter. There's some alpha star for which this vortex line is non-trivial. But using this this kind of anomaly alone doesn't tell you which value of alpha star is non-trivial. It just tells you that there has to be at least one and possibly multiple values of alpha that lead to a non-trivial defect. And actually, in this example, you can show that alpha equals pi is one such non-trivial point, and that is because at alpha equals pi, the symmetry actually enhances from U1 to O2. So there's a charge conjugation symmetry that appears at this special point. And this enhanced O2 symmetry has a defect Tuft anomaly of the kind that I described earlier. So for example, the endpoints of this vortex line, which are sort of monopole operators, half integer, half monopole operators, transform projectively under O2. Sorry, I should have said pi. And so that implies that the pi flux vortex line is non-trivial. And so again, it's non-trivial, but can we say more than just that it's non-trivial? And so here comes a conjecture which will sort of motivate why we think actually that it's conformal. So in 3D, the abelian-Higgs model is actually dual via particle vortex duality to the O2 model. So abelian-Higgs model is particle vortex dual to the O2 model. So this is just the theory of a complex scalar field with quartic interactions. And it's natural to ask, what does this line defect, this pi flux vortex line defect, map to under particle vortex duality? And the claim is that it actually maps to a spin impurity precisely of the kind that we saw in the O3 model. So just schematically write that as follows. So it's a spin 1/2 spin impurity. So we couple to a qubit on a line via the following coupling. Created over time. Okay, and
Sorry,
yeah,
can I ask a question?
yes,
So if we change the spin from 1/2 to higher, like 3/2 and 5/2, do we get like different vortex with different fluxes at the abelian-Higgs model?
good. So the answer is probably not. So the conjecture actually about this vortex line is that, for alpha equals pi, it flows to a conformal line. And then for alpha not equal to pi, it becomes trivial.
Hmm.
So there sort of is no other vortex line that it could flow to. Um, there is a kind of silly formula that you could write down for what the dual of these higher spin impurities is in the abelian Higgs model, which is that so part of the dictionary of particle vortex duality is that particles map to vortices. So the
Mm-hmm.
fundamental field phi of the O2 model maps to on the abelian Higgs side to a monopole operator. So again, this is some kind of disorder operator. So it's not a kind of, you can't construct it out of fundamental fields in the Lagrangian, but rather you
Mm-hmm.
construct it by modifying how you do the path integral so that it looks like there's a magnetic monopole inserted at the point X. And so in particular, you can just extrapolate this spin impurity um, across the dictionary and you get an answer. So let's say for general spin S, you'd expect that you get the same thing, um, except replacing the field phi with a monopole operator. So
Hmm.
this is one answer for what the particle vortex dual is of this spin impurity. So one way of saying what our conjecture is that in the special case that S equals 1/2, there's yet an alternative way to describe this left-hand side, which is as this pi flux vortex line. So if you'd like,
I
it's a kind
see.
of IR duality between this spin impurity coupled to a monopole operator and this pi flux vortex line.
I see.
For higher
That's
spin, we
interesting.
don't have like a nicer form that I know of for these higher spin impurities on the abelian Higgs side.
I see. So they are kind of like monopoles with higher spin. Is that how we think about them? Or
No, so over here, the spin here is referring to the spin of the qubit that you're coupling.
oh, it has nothing to do with the monopole.
Yeah, the
Okay,
monopoles
okay.
are just the monopole operators of the abelian Higgs model. They are what they are, and
Ah,
then
okay.
the thing that we're modifying is like it's not even a space-time spin. It's just it's an internal
Mm-hmm.
spin
Okay, okay.
of this qubit that we're
Yeah,
coupling with a
just the
quantum.
dimension, extra dimension increases of the
Yeah,
tensor product, I guess.
right.
Yeah, okay. Thank you.
Good. Yeah, thanks for the questions. Um,
One question, but this monopole can have different charges, right?
Yeah, monopole operators can have different charges. Here I am referring to the sort of charge one monopole operator.
Okay, thanks. And I mean, what about, I don't know, charge 2 monopole operator? What is map 2?
Uh, Sorry, what about them?
In this duality, I mean, in the O2 model, is it mapped to something?
Ah, yeah, what you're asking, what does the charge two monopole operator map to under particle vortex duality? Uh, that's a good question. I guess you have to write down charge two operators on this side. Of course, you can write down things like phi squared schematically, but okay, good. I'm not remembering exactly what higher charge monopole operators map to, but
Thanks.
uh, yeah, thanks for the question. Okay, and since I'm going way over time, let me just say what the evidence is, quickly sketch what the evidence is for this conjecture. So this conjecture we call spin flux duality. Because so the flux side is the abelian Higgs side where you have the vortex line, and the spin side is the spin impurity side of the O2 model. And in particular, a corollary is that this pi flux vortex line is actually conformal on the IR. And the reason is that, so we argued a bit ago that in the O3 model, the spin 1/2 impurity flows to a conformal line defect by invoking the G theorem and defect 't Hooft anomalies. And you can actually use an almost identical argument in the O2 model. So this O2 symmetry has a defect 't Hooft anomaly for spin 1/2, and you can use the G theorem to prove that the spin 1/2 impurity is also conformal. And so if you believe this spin-flux duality conjecture, then that in particular implies that the pi flux vortex line is also conformal. So the evidence is that the symmetries match. So by the way, let me add one more coupling here, which whose significance will become clear in a moment. Let's see. So yeah, so let me consider a kind of deformation of this spin impurity on the side where you use the poly Z operator on in the qubit. So so I claim that the symmetries match. So let's parameterize the vortex lines as as pi plus some deviation away from pi of the holonomy. And so the actually sort of a stronger version of the spin-flux duality conjecture is that this maps to spin 1/2 impurity with coupling gamma. And the coupling gamma is related to delta alpha in some way. So yeah, so the content is that the modifying the holonomy of the vortex line corresponds to tuning this coupling gamma away from 0. So the symmetries match. So when delta alpha and gamma are both turned off, we have an O2 symmetry that's preserved on both sides. That's the U1 magnetic I was telling you about earlier on the abelian Higgs side plus charge conjugation. And on the O2 side, there's charge conjugation, which maps phi to phi star, and also the U1 phase rotations of phi. So both sides, there's an O2 symmetry preserved. And when you tune the holonomy away from pi, or you tune this coupling gamma away from 0, then that symmetry is broken down to U1. Okay. Another point is that the defect 't Hooft anomalies match. So in particular, when the holonomy is at pi and this gamma coupling is turned off, as I said, there's this O2 symmetry, and that O2 symmetry has a defect 't Hooft anomaly of the kind that I described earlier. So in particular, the endpoint operators of this vortex line or the spin impurity transform projectively under the O2 symmetry, and they're degenerate. So if you'd like, you can see this degeneracy by noticing that the endpoint operators are sort of like half monopoles with charges plus or minus 1/2 under the U1 magnetic in the case of the vortex line. Good. Another thing that matches, which provides evidence for the fact that this entire family of defects on the abelian Higgs side maps to this entire family of defects on the O2 side, is that the anomalies in the space of defect couplings match also. So on the abelian Higgs side, we saw that as you pump alpha by 2 pi, if you're coupled to a background gauge field, then that the 2 pi periodicity is violated. So you don't come back to yourself, you come back to yourself up to a phase. This was what we called an anomaly in the space of defect couplings. A similar thing happens on the O2 side. As you pump this gamma parameter from minus infinity to infinity, if you're coupled to a background gauge field for the U1 symmetry, you find that the partition function again doesn't come back to itself, but rather comes back to itself up to a phase, the same phase as we saw on the abelian Higgs side. So in other words, the anomaly between this alpha parameter and the U1 symmetry is recapitulated on the O2 side as an anomaly between this gamma parameter and the U1 symmetry. And finally, the sort of phases match. So what do I mean by this? So you can consider what happens to the vortex line as you deform the bulk mass, let's say in the abelian Higgs model. This is the last thing I'll say and I'll stop. So good. So as you tune the mass to be very positive in the abelian Higgs model, what happens? Where's the action? Okay, here's the action. Well, you simply gap out this this charged scalar phi, and so you're just left at low energies with free Maxwell theory of a free photon. That's what the phase diagram looks like over here. At some point, you undergo a phase transition as you tune the bulk mass to very negative values, and via the Higgs mechanism, on this side, you end up with a trivially gapped theory. In between, there's a CFT at this fixed point. So what happens to this V pi, this vortex line? Well, it's also conformal at the fixed point, as we just described, or that's the conjecture at least. And you can just calculate what becomes of it in this trivially gapped phase. And there's not much that it could flow to in a trivially gapped phase. Basically, the only option it has is to be decoupled, and that's indeed what happens. It becomes a decoupled qubit. When you flow to the free Maxwell side, it actually flows to a topological line. So free Maxwell theory has an emergent one-form symmetry called the electric one-form symmetry. And that is a U1 symmetry, which in particular has a Z2 subgroup. So there's some topological line operator in free Maxwell which implements the Z2 electric one-form symmetry. And the claim is that this vortex line V pi flows to this one-form symmetry. And you can show that a very similar thing happens on the O2 side, as you tune the bulk mass. So there's a fixed point somewhere in the middle. Now, when you tune the bulk mass to be very, very positive, you just gap out the entire theory and are left with a trivially gapped phase. As you tune the mass squared to be very, very negative, you spontaneously break the U1 symmetry, and you're left just with the theory of the corresponding Goldstone boson, which is a compact boson. So if you'd like, this phase diagram is sort of inverted with respect to this one. So positive mass squared in the O2 model maps onto very negative mass squared in the abelian Higgs model. And you can track what happens to this spin 1/2 impurity at gamma equals 0 as you tune this bulk mass. So again, we know that it's conformal at the fixed point. And you can show again that in the trivially gapped phase, it just simply decouples, more or less because it has no option to. no option but to. And in this compact boson phase, so sorry, I should have said, you might look at this and think, oh, these phases don't match even in the bulk. But it's known, for example, that by a generalization of T-duality to 3 dimensions, that the free compact boson in 3 dimensions is T-dual to free Maxwell theory. So these are actually the same theories. And compact boson has a one-form winding symmetry in 3 dimensions. And the claim is that the spin impurity flows to the topological line operator that implements the Z2 subgroup of the winding symmetry. And winding symmetry under T-duality is exchanged with this electric one-form symmetry. So in other words, basically, if you look at the phase diagram as you vary the bulk mass in both theories, you get the same sort of picture emerging. And so these are the common things that people check in order to check a duality. They check the symmetries match, they check the anomalies match. Here, the interesting point is that we were able to match this kind of interesting new kind of anomaly. It's an anomaly in the space of defect couplings. And then they also checked that the phases match. The phase diagrams match on both sides. Okay, so just to conclude, so we sort of discussed how to use various tools in quantum field theory in concert with one another to learn things about defects. And along the way, we introduced some kind of new kinds of anomalies, like these anomalies in the space of defect couplings. And so maybe the highlight examples were proving that this spin 1/2 impurity in the O3 model has to be a conformal defect. And another application was using these anomalies and various other tools to provide evidence for the spin-flux duality conjecture that relates vortex lines intervealing Higgs to spin impurities in the O2 model. Okay, so that's all I have to say. Thank you.
Thanks a lot for the great talk. I have a lot of questions, but maybe I should allow others to ask first, then I can ask you.
Sure, sure.
So if anyone has any questions, just go ahead.
I have a question.
Uh-huh.
How can we argue that for the vortex, alpha different from pi, we flow to a trivial defect?
That's also a bit of a conjecture. Yeah, the intuition for it is basically that you have some beta function. So here's pi, here's 0. And we sort of know that this defect should be unstable as you deform away from pi. And kind of there's no, like the topology of this phase diagram suggests that there's sort of nowhere else to go but to go to 0. So that's a conjecture about what happens, that this pi flux vortex line is an unstable fixed point if you don't impose any symmetry, and as you deform away, the line sort of disappears to the trivial line. Another way to argue for it, if you believe this spin-flux duality conjecture, is that in the O2 model, you can just sort of see that as you tune gamma to be very, very large in either direction, the line defect becomes trivial. And so that should map across to the statement that you asked about under the spin-flux duality conjecture.
I see. Thank you.
Yeah, thanks for the question.
Any other questions? Okay, maybe I can ask now. So in the fourth line, you were comparing the phase diagrams. When we look at the abelian Higgs model at the minus mass square, we kind of get like these dynamical solitons in the spectrum. And it seems to me like these dynamical solitons are very related to these vortex lines. But what is the corresponding object in the O2 model for these dynamical solitons?
Sorry, can you remind me about this?
So like
Which solitons do you have in mind?
the Abrikosov-Nielsen-Olesan vertices.
Uh-huh.
So what is the corresponding object for O2 under the particle vortex duality?
So by the way, are these solitons at the fixed point? I'm trying to remember.
I think it's
Probably just in the
negative mass
gap.
squared.
Yeah. Okay. Um, so I'm not, so that's a good question. I'm not sure if there need to be yeah, I'm not sure that these solitons sort of need to be reproduced in the O2 model. Part of the reason is that so this particle vortex duality is what's called an IR duality. So the only thing that's being claimed here is that the theories match once you flow to very long distances. And at very long distances, the theory is trivially gapped. And so these solitonic objects you're talking about are sort of, I think you should think of them as objects that are there when you're not all the way in the IR, but it's like slightly above it. And it's not exactly clear to me that they need to be reproduced in the O2 model, although I'm not 100% sure. So maybe let me think about that and get back to you.
But it kind of feels like the vortex line that you have is the word line of the vortices. That's why I was like asking maybe there should be something corresponding. Because they also induce the same holonomy. They also have the winding, so
Right. So yeah, so there, I mean, so the way, yeah, so the way that we argued that you get a decoupled qubit in this very negative mass squared phase of the abelian Higgs model is actually sort of, we argued semi-classically by arguing that if you insert this vortex line and you look for classical solutions of the equations of motion, then you find A and O like solutions that are sort of doubly degenerate with each other, two degenerate A and O solutions. So that's okay. They're not quite the ordinary ANO solutions. They have these modified boundary conditions at the origin due to the vortex line being present. So I guess you're asking, like, do these ANO solutions have any avatar on the O2 side?
yeah, kind of.
Yeah,
But I don't know if any topological object exists in the O2 model that can behave like that.
right. So the first order answer is I'm not sure, and I should think about this. But my instinct, which might be incorrect, is to say that just as the sort of ANO solutions themselves, without the vortex line present, don't necessarily need to have an avatar in the O2 model. I think it may also be the case that these here in the presence of the vortex line also don't need. But it's a
Yeah,
very
that
nice
sounds
one.
convincing. Yeah.
But I'll think about it more and get back to you. I'll send myself an email.
Okay. Thanks. Because these are the kind of things that I'm very confused about also.
Right.
So another question I wanted to ask was like, so when we are talking about these anomalies in the space of coupling constants, I always think of -1 form symmetries. But for defects, how can we think of them as -1 form symmetries? Like, are they symmetries on the word line of the defect, some effective theory, and we look at the -1 form symmetry and the anomaly? or there is no interpretation like that for these anomalies in the parameter space.
Yeah, so for the good. So for the anomalies that I discussed in this talk, at least, you can basically think of them in more or less the same way as ordinary anomalies in the space of coupling constants in quantum mechanics. So in other words, like the things that label anomalies in the space of line defects are precisely the same things that label anomalies in the space of coupling constants in 0 plus 1D quantum mechanics. Um, at least for the particular anomalies that I'm discussing now. There might be sort of anomalies beyond the ones that I'm discussing that don't satisfy this. But yeah, so essentially, like, I guess what I'm saying is in quantum mechanics, you can have a parameter space or a -1 form symmetry if you like, and a global symmetry, and those things can have some kind of mixed anomaly that you call an anomaly in the space of coupling constants. And from the point of view of line defects, it's basically the exact same story. It's sort of like if you just forget about that the bulk existed and just focus on the line defect, it looks like a theory which has an ordinary symmetry and also a parameter space, and so it can have the same kinds of anomalies as quantum mechanics theories have.
I see.
So that's all that's happening here.
Okay. So we're kind of gauging the parameter, but only along the time direction, not along the space directions. And then
Yeah,
we can see the anomaly.
Right. You can't the parameter is not even defined along this. It doesn't make sense to talk about it along the space direction.
Yeah,
It's
yeah,
only defined
sure.
along the defect. Yeah, I wouldn't say we're gauging it, just that we're sort of promoting it to a background field, which you can
Yeah.
think of in the same spirit as coupling the -1 form symmetry to a background gauge field. But yeah.
I see. Okay. And one last question I wanted to ask. I think I also asked this to Zohar, but when you consider the abelian Higgs model with the scalar that has non-unit charge, like let's say it has charge Q under the U1 gauge group, how does the story change? Like the spin-flux duality and the bosonization, particle vortex duality, all these things.
Yeah. So we didn't think about that case. Of course, to first order, so you'll still have the same anomaly in the space of defect couplings. And I think you'll have the same defect Tooft anomalies as well. And the thing is, I don't know of I don't know of a dual description of abelian Higgs with a charge 2 scalar. That could be my own ignorance, but I think it's not part of this duality web. So there probably won't be an analog of a spin-flux duality. But maybe you could still try to argue about the IR phase just in the abelian Higgs side using these kinds of ideas and come up with a compelling conjecture. There is, of course, an open question which we'll probably try to think about soon, which is that, there's this well-known story of many years ago that these particle vortex dualities tend to fit into a web. So once you have one example of a particle vortex duality, usually you can obtain a whole host of other examples by applying some simple transformations to the theories on both sides of the duality. And so you can ask basically whether spin-flux duality also can be elevated to a web. That is, like, you can find some kind of dualities involving these conformal line operators inside other examples of particle vortex duality. So that is that we haven't thought about yet. But
I see. And I was also curious about this because at some point you said that there's a conjecture that the O3 model does not have any one-form symmetries. So like if it doesn't have any one-form symmetries, naturally there wouldn't be any particle vortex tools to abelian Higgs model with, like, let's say charge 2. because then in that case we have Z2 one-form symmetry with the Wilson lines, but on the O3 model we don't have that. That's
Yeah,
also why I asked about it.
yeah, no, I don't think O3 is dual to a billion Higgs with charge to matter.
Okay.
Actually, I'm
Okay.
sure people have studied this, but I don't quite know what the properties like. I don't know if it's a second order phase transition as you tune the bulk mass and charge to a billion Higgs. Zohar has a paper on this, so I'm sure the answer is there, but
Okay. Any other questions from the audience? Maybe we can stop the recording, and sometimes people want to ask questions off the record.